Hello everybody, I am Dr. Utku Buyuksahin from Sensobright Industries LLC. Today I will talk about our company, a general introduction about tactile sensors and about our patented technology BTSS, which is the short form of Buyuksahin Tactile Sensing System. Now I'll talk a little about the company, our company. God bless you. Sensobright Industries LLC is a technology-oriented small business company with an innovative concept. Sensobright has teamed up with Inventram to ramp up commercialization and develop tactile sensors technologies. Inventram is a wholly owned subsidiary of Koç Holding, which is a Fortune 500 company. In the fourth quarter of 2015, Sensobright will continue to its operations in Portland, Oregon, with an investment of over $5 million. Thanks to him, he introduced me, so I passed this part. I only will show the relevant publications about this project, one international patent, one international book chapter, and 2 international conference papers. As it's mentioned in my CV, some examples of former projects: 3D CNC milling machine, 3-axis, 6th Stewart platform, for 8D cinemas, etc. Buyuksahin Tactile Sensing System is a prize-winning technology. Technology has awarded many prizes from technology contests and got many prizes from ministers to military commanders, from university directors and company CEOs. Also, has been broadcasted in TV shows, primetime news, technology programs of highest rating TV channels, and also published in many newspapers and prestigious technology magazines. Now let's talk about tactile sensors. I think everybody knows, but I'll briefly introduce. It's well known that automation mimics the human body. Sensors are copies or receptors, as well as computers are copies of the human brain. As the biggest sensory system of the human body, is its skin that covers the body. Tactile sensing is useful in wide variety of haptics applications for robotics and automation. There are 2 types of tactile sensing, kinesthetic and cutaneous. Kinesthetic is the feeling that we sense from our muscles when we hold something, and cutaneous is the feeling with our skin. Most of the former robotic systems and devices can only provide the equivalent of kinesthetic sensing with force-torque sensors. Later ones use tactile sensors in order to extract property of environment and interaction using only cutaneous information acquired from these sensors. Flaws of tactile sensing systems, former systems, are summarized as follows: short number of tactile sensing unit element per measurement area. I will mention about this later. Low spatial resolution, high cost for data acquisition for excessive analog inputs, computational burden, bulky structure, noise arising from analog measurement, perturbation problems at high magnetic fields. Sensobright's technologies provide a solution to a problem of current dexterous hands grasping manipulation systems. Due to our patented innovation, the number of the tactile sensors, sensory receptors per centimeter square can be increased up to 1 million. The key features of the system are a very high resolution, over 1 million per square centimeters, force, shape, temperature, and multi-touch information, skin-like flexible design, compact data transfer, low power consumption, over-the-counter components, and no interference. Let me explain this a little bit more. For average human, there are 241 sensory receptors per centimeter square in the fingertips. So, in average human, there are 241 tactile receptors in the dentist area of human in the fingertips. So the point was to acquire that level of tactile sensing to simulate the human body. But with our technology, we improved with 4,000 times more, and we can put over 1 million receptors per centimeter square. We can get, pardon? Over 1 million per centimeter square. Yes, yes. Force, shape, and temperature. Yeah. Yeah.
You want one of these?
And it's a skin-like flexible design. Every component of the sensory made up with flexible material, and so we can cover all the non-uniform shaped robots or something, everything. Also, the patented project covers the data transfer part of it, and now we achieved that up to 50 million sensory data to the computer with only one USB cable. And we can send every sensory data individually, not serially. Individually, we can send all the data individual, and it does not saturate from other data. Yeah.
Can you determine where this contact has been taking place when you have the sensor surface?
Yes, yes. I will show the videos of working.
You do a lot of bin picking, so we are, I would
Yep.
say, number 2 or 3 in the world bin picking companies. Right, because we are making manufacturers.
Yes, this
this
is very brand new.
How we have ripped apart finally. Oh, this is interesting. Okay.
This is very. And low power consumption, and another big part of the technologies, we use every component over the counter components. We don't produce any component of this sensory pack, so we can acquire the components everywhere in the world. So it's the big amount of production line is not a big issue for us. And it's optical based product, so there's no interference as we carry the force, stress, and temperature data with by the light. So if there's a black hole, yes, we can't work it. But unless there's not a black hole, it will work because of the light. Photons does not change their way. And performance test results, we made the results, we made the tests with 3.2 GHz processor, and all the number of receptors per centimeter square, all limited to CMOS CCD frequency that we used. And sensitivity test results give us, we used a 23 centimeter square Buyuksahin tactile sensor system in the test. And we have a delay of 16 milliseconds, but this can be improved. And the resolution of 0.0612 newtons, and which is about 6 grams. And this can be improved by changing the elasticity of the silicon pads that we used. And this is the, this area is active now, and you can see the touch data here real time.
It's optical, so there's like an array of fibers.
Yes, yes. And working principle of the system, as we know, former applications use optocouplers. One sends lights, infrared or regular light, and a reflected plane, and the phototransistor gets the data. When we change the distance, this one receiver gets a brighter image, and you can determine, you can calculate the distance from here. But this is too bulky because these are about a total of 5 millimeters both. So the spatial resolution is very short in number. So we put fiber optic cables to here. As we know, fiber optic cables are 9 microns diameter each, today's world. So we can put over 1 million, exact number is about 1 million and 1.5 million, something like that. But as the fiber optic cable technology rise, this number will be risen also. So with the fiber optic cable, we can make the spatial resolution very much. But if you get too many over 1 million data to the computer, want to get that data, as you know, if you use a data acquisition card with inputs of 64 inputs, if you have 2 million receptors data, so you have to use about 32,000 data acquisition cards. So that's impossible. If possible, it costs over 5 or 10 millions. If you can put this into a computer. So here comes the solution of it. So I don't change the this data to phototransistors voltage data. I use optics. Here sends and receives a brightness. So when I put this, every fiber optic cables and to a CMOS pixels. So with a high definition pixel, 1920 x and 1080 plus them, it means that 2,073,000. So I put this distance data with the brightness of an image of every pixel. So sent to the computer with a photo frame. And when I use HD webcam, I sent 30, that means 30 hertz of data, and I can send 2 million. And we know now we have 50 megapixels of USB CMOSs. So we can send 50 million sensor data to the computer with only a USB, or maybe you can use multiple USB connectors, so you can connect too many USB cables to a computer, so this volume can be.
You said it's 60 milliseconds.
That's delay time of our software. It's about the software, so it can be improved by the time. Now the tests gives that real product gives that results, so it can be improved. If I use a high velocity camera, 100 fps, then it will be 100 hertz. 1000 fps, it will be 1000 hertz. And this is the example, stimuli, cylinder-shaped stimuli. When we put, and we use a silicon pads over here, because we can, more penetration gives a brighter image. We can calculate the distance here, and when we use a silicon pad here, that we know the elasticity of the silicon, so the penetration value will give us the force here. So we can calculate the force, and this shape will sense the computer this image. As you see, brighter ones, no penetration, black, and less penetration, black, more penetration, white, and we can then image processing, do the image processing, then calculate the penetration.
So the force you measure is related to the elastomer degree?
Yes.
Elastic degree?
Yes, of course.
Shore hardness, or how do you measure? You measure then in shore hardness of the elastomer?
No, not shore. Shore is, as you know, about the output part. The elasticity part of whole the material. Yes. And here is the part. As we said before, more penetration gives a brighter image. So with the brightness, we can calculate the penetration value. With the elasticity phenomena, by the Young modulus of the silicon, we can calculate the applied force from penetration value. And with the total pixel number of brightened images, we can calculate the area. We can only count the pixels, and we can calculate the area of the penetration. So finally, we can calculate the stress from force over area. And as I mentioned before, we can do this for every individual receptor because we send each receptor's data individually. And here's another example. Finger is stressed. System sees, camera sees like this, the fingertip. Then image processing is done. It shows, and then this is for another study. With a MATLAB program, we use some filters on it, and we can soften it or more accurate or more soften. We can do it. And here, a sharp object is penetrated. It shows on only. And as we don't have too much time, I will pass this very fast. These are some of the photographs from manufacturing steps. We produce our silicon also. And the most challenging part is the fiber optic cable setting. And we did a fiber optic cable setting machine. Here some examples. Here it's visible fiber optic cables, not 9 microns. It's about 500 microns diameter. So normally it's very thinner. Here 64 per centimeter square, 104 centimeter square, 256 centimeter square, and here what it looks like. 256 centimeter per square, and that's it.
So could it detect without force? If it just, say if I put it on the outside of this bottle, could it tell me where the water was?
Water, we can feel it with the temperature. Yes, and also we use infrared CMOS to get the temperature data. So it's not a big issue for us cool. to feel the, where water is.
Yeah, nice.
Okay, final question, where are you located? In the US or?
Now we are located in Turkey, Istanbul, Turkey, but in the fourth quarter of 2015, about 3 months later, we will be continue our operations in Portland, Oregon, with an investment of over $5 million.
So I will send you an R&D guide to Turkey, because we have a Turkey office.
Yeah.
Millions of questions, because we are developing gripper systems where
yes.
we need to sense forces and
yes.
temperature.
Yes.
And we are looking for sensors which are applied to surfaces. Even if we grab something, we need to get the forces to our control unit. So this is positive. Perfect.
Thank you. Thank you very much.
Thanks a lot.
Have you tested it for particles?
Particles, what kind of?
This is in semiconductor, we're always interested in where the wafers, because we can't grab the wafer because it creates particles.
Yep.
We want to know where the wafer is on the end effector.
Yes, we can, as I mentioned before, we can change the silicon's Young's module.
Yep.
When we use very softer silicon, we
yep.
can feel more
subtle,
more my English finished now.
A lighter object.
Yes, lighter objects.
More sensitive.
Yes,
What's
more.
the minimum sensitiveness you can go down?
I don't I can't now say what's exactly because we have to try because we have to produce silicons and
Different for
yes, of course.
Good technology.
Yeah, very interesting.
And
Go ahead.
sorry. And this morning we had a breaking news from our Japanese patent attorney, and we learned that in Japan it's patented today.
Nice.
And
congratulations.
thank you. Published and patented. Yes.
You need your business card.
Well, thank you very much.
You're welcome.